Welcome to Maths with EJD. We're still talking about differential equations, and we've been talking about linear ordinary differential equations. I mean, generally, first order ordinary differential equations. Now we're talking about linear first order differential equations that we can solve using integrating factor. So let's go straight to talk about the general form of such an equation. General form. In the previous video, we had looked at the separable ordinary differential equation, and we saw its general form too. So for this one now, a linear first order differential equation has the form dy dx plus p of x y equals q of x. So you want to check to be sure all these components are there. You have it's first order for sure. So you have dy dx or y prime plus p of x y. So you have y with a coefficient, whether it's if it's one, then you just have y. If it's zero, then you don't even have y at all. And then it is equal to something that is a function of the independent variable x. So that's the general form. So from here, we need to understand that p of x and q of x are functions of x. They're functions of x. And then we also know that dy dx is the first derivative. Of course, we are talking about first order, so we don't have more than first derivative. So it's the first derivative of y with respect to x. Okay, so I think it's important to know in what real life applications do we have this kind of linear first order differential equations. So real life applications. Okay, so linear first order differential equations are commonly used in one. We have Newton's law of cooling. Newton's law of cooling. Okay, so here you have dt plus kt equals kt env. I think that's the environmental temperature. So this describes how an object's temperature approaches the ambient temperature. Okay, that's the Newton's law of cooling. So it describes. Should I talk? I think I should mention that it describes how an object's temperature approaches the ambient temperature, approaches the ambient temperature. So it means that if you bring an object into an environment, okay, so the rate at which that object normalizes with the environmental temperature is what this equation shows us. Approaches the ambient temperature. Okay. So let's assume that the temperature in a particular room is 20 degrees centigrade, and you bring a metal that is like 105 degrees centigrade hot. So if you bring it in, so this equation describes how the rate at which the 105 degree centigrade metal cools to attain the same 20 degree centigrade temperature in the room. Okay, that's what that is about. Now let's talk about the another one, talking about electric circuits. Electric circuits. Okay, so here we have L, the I, the T plus Ri. So you see here, I is the independent variable. I mean, I is the dependent variable while time is the independent variable. So L di dt plus Ri is equal to V of t. Okay. So these models an RL circuit, an RL circuit where I is the current, where I is the current, L is inductance, L is inductance, L is inductance, R is resistance, and V of t is voltage. V of t is voltage. Okay. And then we can also talk about another example, which we even saw in the other situation. So we can have, though it is variable separable, we can also show it as a linear form, right? As this linear form we're talking about. So we have radioactive decay, okay? Radioactive decay. So when you have the N, the T, plus lambda N equals 0. Another way of writing this would be the N, the T equals minus lambda, and that's the kind of thing we saw when we talked about separable equations. Okay, so but in this form it actually resembles the first order we're talking about. So, and what does it do? It describes, so here it describes the decay of a substance the decay of a substance over time. Okay, so we have a whole video dedicated to this whole idea. So we'll talk about that later. So let's move on to consider okay, let's look at method of integrating factors. Method of integrating factors. Okay. Okay, so to solve that equation, that first order linear equation, we have dy dx plus p of x comma y equals q of x. This is the general form that you saw already. To solve that, so we use an integrating factor. So what we call an integrating factor. Okay, if. We use an integrating factor, and this is how the integrating factor is described. We use an integrating factor. Mu of x equals e raised by integral of p of x dx. So if once you've identified this p of x here, then you can use that to get the integrating factor. So let's look at the step-by-step approach to this particular integrating factor thing. Okay, so step-by-step solution. Okay, so the first thing is to compute the integrating factor, which we have just shown now. To compute the integrating factor, after that, I'll just call it IF. So the integrating factor mu of x is equal to e raised power the integral of p of x dx. That gives us the integrating factor. So that's the first thing. The second thing we want to do is to multiply the entire equation, multiply the entire equation by mu of x, that's the integrating factor, to make the left side, an exact derivative, So that's the next thing we do. So in this case now we have mu of x multiplied by dy dx, okay, plus mu of x multiplied by p of x y. So you see the normal equation, and we are multiplying through by mu of x. Then you have mu of x multiplied by q of x, like that. So that now you see that this whole expression can then become d dx into mu of x y, okay, and that is equal to mu of x q of x. So if you look at this now, so by the time you resolve this expression, you discover that this whole thing is going to be d dx of u of x multiplied by y, and that will be equal to u of x q of x. So the next thing we want to do after this is step 3. So in step 3, we can now integrate both sides. So integrate both sides. So looks like before you finally solve for the function you're looking for, integration is the last thing you do. So if you integrate both sides now, so it's more like you have integral of d dx into mu of x y, okay, equals integral of mu of x q of x dx, of course, with the constant of integration. So, and of course, when you do this kind of integration, right, you see, okay, here you have d of x. Yeah, I should talk about this. So this is more like d of x equals this. So this cancels this, right? Right. So you now have integral of d u mu of x y, okay, equals integral of mu of x q of x dx plus c. And whenever you have integral of d something, the result is just that thing. The d just goes away. That's the only thing that happens. So here now you have mu of x y is now equal to integral of mu of x q of x dx plus c. So that means that y alone, which you're looking for, that when you solve for y now, okay, okay, I think the next step is to solve for y. That's like step 4. Finally, you solve for y, which you're actually looking for. Solve for, now you're looking for y of x. So from what you have there, you have mu of x y equals integral of mu of x q of x dx plus the constant of integration c. So y alone now is you divide through by 1 over mu. So you have 1 over mu of x. That's 1 over mu of x integral mu of x q of x dx plus c. So that this is more like what you end up having. Okay. So that's the whole idea of integrating factor. Now let's talk about an example. So imagine that you have this example. You want to solve dy dx plus 2y e raised to power x. Okay. So so we take the first step. So we say step 1. For step 1, you identify p of x and q of x so that you can see them. So what we have is dy dx plus 2y equals e raised to power x. So if you compare this with the general form, which is dy dx, okay, plus p of x y equals q of x. So what do we say? We can conclude then that p of x is what we have with y. So you have p of x y, there you have 2y. So it means p of x is simply 2. And then q of x is just this right hand side, e raised to power x. So you have q of x to be equal to e raised to power x. So easily done. And once that is taken care of, we can go for step 2. So in step 2, what do? You compute the integrating factor. Compute the integrating factor. Compute the integrating factor. And that means you have mu of x equals integral of p of x dx up there, and that means you have e raised to power integral of p of x is 2, so you have 2 dx, okay, and that is equal to e raised to power. If you differentiate, that's more like 2 integral d of x, right? And just like I said previously, if you integrate d of something, you just get that thing. So this is e raised to power 2x. You don't have to worry about the constant of proportionality here, okay, because it's not necessary for now until you get the final result. So our integrating factor here is e raised to power 2x. Done. And then we go for step 3. So in step 3 now, you multiply through Step 3, multiply through by mu of x. Okay, we multiply through by mu of x. So the original expression again is dy dx plus 2y e raised to power x. So we multiply through by mu of x, and that means you have e raised to power 2x dy dx. Okay, then the other one you have 2y. So that will now be 2 e raised to power 2x y, and that is equal to um okay, well, let me not be in a hurry, right? So multiplying through by e raised power 2x. So you have e raised power 2x and then e raised power 2x again into 2y equals e raised power 2x into what we had there before was e raised power x, right? Yeah, e raised power x. So let me go step by step like this for easy understanding. So now we have e raised power 2x dy dx plus 2e raised power 2x. When we multiply all of that together, 2e raised power 2x, and that is equal to e raised power 2x times e raised power x. That's e raised power 2x plus x. That's e raised power 3x. Now, with this in place, now we can now go ahead and, of course, from what we saw up there, right? This whole expression is simply the same thing as d dx, okay, of e raised power 2x multiplied by y. All right. So that's what that simply means. And that is simply equal to e raised power 3x. Now, of course, this makes sense, right? If you differentiate this expression with respect d dx of e raised power 2x, for instance, that will give you if you keep y constant, so you have y here, differentiate e raised power 2x, you get 2 e raised power 2x. That works. And then the other side is e raised power 2x is kept constant. Now differentiate y, you get dy dx. So that's perfectly correct. So with that in place, we can go for step 4. Step 4. In step 4, you integrate both sides. So the integration becomes easy now that you've multiplied through by the integrating factor. Integrate both sides. So that means you have integral of d dx of e raised power 2x y dx, okay, equals integral of e raised power 3x dx, basically. And then, of course, dx cancels dx. So we have integral of d, if you like, y e raised power 2x, okay, equals integral of e raised power 3x dx. So if you integrate d of anything, that thing remains. So we have y e raised power 2x equals, when you integrate e raised power 3x, differentiate 3x, you get 3. So that 3 comes as inverse to multiply. So we have 1 over 3 e raised power 3x plus the constant of integration c, basically. And at the end of the day, right, you now need to solve for y, okay? So that should be step 5. So we've got this expression now, but we need y at the end of the day. So when you solve a differential equation, you're always looking for the dependent variable y, or whatever you call the dependent variable. So the dependent variable, it could also be x of t. So in that case, we'll be looking for x, but here we're looking for y. So step 5 tells us to solve for y. Okay, that's y of x. So the way to do that is you have y e raised by 2x equals 1 over 3 e raised by 3x plus the constant of integration c. So since you are looking for y, and the only thing disturbing y is e raised by 2x, so you divide through by e raised by 2x. So we have y e raised by 2x divided by e raised by 2x, and that is equal to 1 over 3 e raised by 3x plus c all over e raised by 2x that you're dividing with. So that means we have this cancelling out, and then y is equal to 1 over 3 e raised by 3x all over e raised by 2x, then plus c all over e raised by 2x, okay? So that means we have 1 over y equals 1 over 3 e raised power 3x minus 2x. That's e raised power x up there plus c e raised power minus 2x. And this is what we have. Okay, this is what we have. So in conclusion, right now, so we can say thus general solution, the general solution is the general solution is y of x equals 1 over 3 e raised power x plus c e raised power minus 2x. So this is general solution. Since you don't have an initial condition, we don't worry. We cannot have a particular solution. So You see, this method is systematic and applies to any linear first order differential equation. So it applies to any linear. So another thing we just want to do is, as usual, we want to visualize this solution, because now it is general solution. So it's a family of solutions, and it is going to be dependent on whatever value you give for C. So you have y of x equals 1 over 3 e raised power x plus c e raised power minus 2x. So since we don't have an initial condition, right? So we are going to have this as the family of solutions based on whatever the value of whatever value c takes. So let's try to visualize this. So we have 1 divided by 3, then we have e raised to power x, then we have plus, of course, the first thing I like to do is I'll just say c e raised to power minus 2x. Okay. Now we can make a slider on this C now. So as you slide this C, you see that it's, so as it goes to -10, see what it looks like. As you move it, so when it gets to what does it get to? When it gets to 1, right? At 1, this, see, it's like a parabola. And then if you keep at it, it now shrinks as C increases, and then it just keeps shrinking. But here at 1, right, it becomes, so it becomes a parabola at 1, okay? So at 1 it's a parabola. So as it keeps stretching it, so the parabola keeps expanding, and then it becomes like this concave thing you see, and then it can keep going, and then at -10 it just rests around there. So it's more like it can be this outstretched thing at -10, and it can be just a shrunk parabola at 10. Okay, so another way to visualize this is this: just change the values of c. Let's assume if the value of c is 1 here, this is what you get. Then, okay, let me do my normal -3 to 3 thing. So this is -3. This is what you get at -3 when c is -3. This is what you get when c is -2. So this is what you get when c is -1. Okay, this is what you get when c is 0, right? This is what happens. When c is 0, see what you get when c is 0. And when you come here, that's when c is +1 now. See what happens. Okay. See, when c is +1, that is what you get, that green, that big green thing now. Then when you bring it here, so now once it's positive, it starts becoming that parabola. And then if you come here, what about when c is +2? Okay, when c is +2, it's that purple. Then when c is +3, okay, see what you have. So the threshold is like from 1, right? It begins to take that parabola. When a c is +1, it begins to take, because it becomes a parabola basically, and then it keeps shrinking like that. So all these are solutions to that problem, and that is why we said it's a family of solutions. Okay, it's a family of solutions. And for you to get a particular solution, you need an initial condition or a boundary condition to so where you get to decide the actual value of the um of the expression of the answer. That's the particular solution. So like we said, this method is systematic and applies to any linear first order differential equations. Now, can we look at some practice questions? Practice. Okay. 1, solve dy dx minus 3y equals 6x. So here P of x is 3 and Q of x is 6x. Okay. And then we have 2, you have dy dx, solve dy dx plus 4y equals 2e raised by minus 2x. So here, P of x is 4 and Q of x is 2e raised by minus 2x. All right. Then 3, you may also want to solve dy dx plus y equals 3x squared. So P of x is 1, while Q of x is 3x squared here. Number 4, how about solve dy dx minus 5y equals 7e raised to power 3x. So q of x here is minus 5. Pay attention, it's minus 5, not just 5. And then q of x is 7e raised to power 3x. Then question 5. How about solving solve dy dx plus 2y equals 10 sine x. Okay, so p of x is 2 and q of x is 10 sine x. And lastly, question 6, you want to solve dy dx plus 5y plus 5y, right, equals 3x squared. So here p of x is 5 and q of x is 3x squared. So try your hands on this and let me see your answers in the comment section, whether on Facebook or on YouTube. Feel very free to try your hands on them. Let me also know in the comment section how helpful these videos are for you. Let me know if there's a topic you'd like me to teach, a problem you'd like me to solve. Then if you have subscribed to this channel, thank you. If you have not subscribed, please go ahead and do that, because there's so much more coming your way as far as differential equations are concerned. And there are many things on the channel already. You can benefit from matrices, vectors, set theory, all kinds. Yeah, graph theory, network theory, generating functions, statistics, probability, a lot right there. So you don't want to miss out on any of that. So subscribe and hit the notification bell so you can always get alerted each time a new video is released. And don't forget to like and share so that more and more people can have access to this great content. Till I come your way again, keep doing maths right. Watch out for the next method we'll be using. I think I'll be talking about Bernoulli equation next. I think. So bye.